Okay, so the purpose of this video is kind of address some questions people had about the source filter model, and specifically once we used, so we're talking now about class 6. Maybe I'll make it full screen so I can switch more easily. So specifically, about representation of formats by zeros, okay? Now, I mean, one of the reasons I chose to address this, besides the fact that speech and voice production are very much part of deep learning today with audio and music, and I think there is a big opportunity to create expressive voices, singing, popular music. The use of voice is really dominant. So, and the expressivity of the voice becomes something very personal, right? We might even like very harsh voices or very specific voices, and the ability to create, for those who are less familiar with, let's say, the um, Vocaloid, yeah, the project. It's actually came out of a computer music lab in Barcelona, Xavier Serra, who I think again that's one of the major music companies. I think Yamaha kind of either bought it or sponsored it. But now, like in Japan, there are these Vocaloids. You can buy a software with a specific name of this virtual performer musicians, right? Well, it's a performer in the sense singer, not a performer on a musical instrument, but and there are concerts with these avatars singing, and each one has its own voice, and there is actually a lot of effort to edit. You actually have a very detailed control there or of the articulation and how you prepare the voices. So it takes a long time to actually render credible voice, but the synthesis method itself gives very unique results. So people kind of maybe started as Japanese culture, but I think it keeps on coming up more and more. So anyway, I don't have to motivate you too much about the idea that singing and expressive speech are going to catch more and more. And of course, as part of, if you want, deepfake, anything. Specifically going back to the questions. So source filter models, I hope everybody understands kind of that motivation. And again, the new models are much more detailed, but the basics of signal processing, that was an opportunity kind of to describe this. And if we think about trying to model this filter, so all of this boils up in the early stage or the early models of voice to basically passing either a buzz, basically either a very periodic harmonic, almost perfectly harmonic. I mean, usually you have this trend, but you can even think about this being flat and kind of getting this curve up to compensate here on the formants. So anyway, you have some kind of excitation, which can be either pitch or it can be noise. So this can be flat, just noise. And then you shape this into these formats, right? So that was the whole idea, that the vocal tract here takes the vocal folds or the buzz or the noise, the hiss. So if it's voiced, it's this buzz. If it's unvoiced, it's a hiss, and it goes through here, and you need these formants. So the whole notion of modeling this in some kind of mathematical way was where we introduced the concept of filters. The formants are what we were trying to produce. This is the perceptual aspect. And then the question is, so how do we model the filter? This is where I introduced, and I would like you kind of to be familiar with the terms of filters, although we're not going to ask too many details about, what this filter is, but in convolution, we showed convolution earlier, and that was basically this forward path. You basically have an input going through a bunch of amplifiers here. The triangles are the amplifiers, and T would be the delay. And that was the forward filter. This is the convolution, and I'm sure everybody now doing convolutional neural networks, and the concept of convolution is really popular now. In audio filters, there are these autoregressive filters, and you might also come up and hear about autoregressive in neural networks as well. But what the autoregressive means is that you basically go and you send the output back. Okay, that's the feedback. And this going output back, you pretty much just flipping this structure of the usual convolution filter to apply this backwards to the outputs. So you have the delays here, and you have these other basically amplification coefficients, or whatever the A's, multipliers. So really symmetric, but then when you kind of chain them together, you get both. You get both the forward part and you get the backward part. So the forward is basically, if you write this now, you can write everything as a difference equation, okay? So if we have just on one here and one here, you basically have the B0 here just going forward. If you had a delay here, you will have B1 with times x n minus 1. If you have another one, you'll have also B2 times x n minus 2, and so on. So this is just the forward part. So y is a function of kind of running average on the axis, but the autoregressive part is this, okay? So basically this y also sees a delayed version of its output, yn minus 1 times a1, and the convention is that these are with minus. Okay, so basically there is a little discrepancy here, because you either, the way it's written here, everything is with a plus, but if the convention is, so yn is basically, no, sorry, that's so yn is these delays, sorry, plus the delays. So there is a little discrepancy here between the plus and the minus. Okay, now we mentioned this idea of Z transform. And I think it helps to understand, or just be familiar, so it's not like shocking that we talk about Z transform. But Z transform is just like a Fourier transform. We just use this abstract Z complex number instead of the exponent, the e to the power of minus j omega t. This is kind of just a complex number, okay? And we do this transform, okay? And the delay is Z minus 1, and there were some previous slides that actually showed why the delay is Z minus 1. So if we accept this fact, and if you want to go back and see how this is translated to this mathematically, it's really just one step. But let me kind of like move forward with this idea that now we can actually go and express these relations, the difference equation, in the Z domain, okay? And then what we want to derive from this is so-called transfer function. So the transfer function is an important concept. We spoke about this, that basically filtering is basically multiplying in frequency. So this whole idea that for linear filters, okay, all of these operations, convolutions, or the AR, which is also the autoregressive thing, they eventually operate for whatever they do in the time domain. In the frequency domain, there are multiplications. There are multiplications between the transfer, the Fourier transform, the Z transform of the input. There is this H, which is the transfer function, and that gives us Y. So basically H, and maybe this is the part that is missing and confusing, H is basically what relates X to Y, or in other words, xz times hz will be yz, or hz is yz divided by xz, okay? So maybe I can try to annotate this briefly. So so if we go ahead with this idea that we have basically y of z is h of z, okay, of z, okay, times, okay, this is that kind of, if you remember, we were showing an image from just a filtering, like an equalizer from some audio software, And it was pretty evident. So you basically draw like a low pass filter, right? So if you have this H and you can specify this, and again, if I can get my mouse back somehow. Okay, so oops, let me go back here. So if you remember, like, you know, we had the low pass filter, this was the drawing of H, and it will basically multiply or give you different weights in the frequency domain over the frequency contents of C. So if you think about this way, or you take these Y's, you move this to the other side, you have Y times A1 Z minus 1 Y, right, is equals B0X, and you divide them, you get the H, okay? And then again, I said, we don't need to go through Z. We could have always used EJ omega T here, okay, to get actually frequencies that have physical meaning, but somehow the idea that we use the Z transform, and now we think about filters as some kind of a polynomials, okay, in a different domain, the Z domain, okay? Kind of a mathematical trick. Once you kind of accept this, get used to the idea, then, you know, it's just like any mathematical tool. Allows you basically to do more things formally and develop stuff. So I'm not saying you shouldn't kind of seek the intuitive motivation, but I think it's also important to accept that this is basically a way for you, with the omega, it does have a meaning. With Z, it's more a mathematical method of representing filters. So we get this frequency response. Okay, so I'm getting a little long, but I hope this explanation kind of gives the motivation. So if we had a more complicated filter, we'll get more basically components on the numerator and the denominator, right? So we have a polynomial on the top and polynomial at the bottom. Just in this case, we have only B0, but in the general case, we get this very complex structure, okay? And basically, these are all the different delays. These are the forward delays. If you think about all of these, okay, they will show up here, okay? And all of these, okay, will show up here, down here, okay? And kind of the G is just to scale it because you might have not necessarily a 1 here, okay? So if you scale everything, okay, or divide all of the coefficients by B0, you put it here. So again, since I was kind of you know, copying and pasting from different sources, I didn't want to start writing these equations, so I apologize again for the change in notation. But you think about B0 as G, and then everything else is divided by this B0. You can write these things or actually divide this one by A0, this one by B0, so you have this fraction here. So as a concept, yeah, I would like you kind of to see from this expression that you can describe any general or so-called infinite impulse response. I don't know if I actually ever mentioned what IIR stands for, but if you go forward, okay, and you input an impulse, okay, this is a way to see what the coefficients are without knowing what the filter is. If you bang it with an impulse, basically, and you don't have this part, you don't have the autoregressive part, and we did mention this before, it's pretty evident to see that, you know, the impulse will basically output the B0, then it'll pass here, output B1, because there's nothing coming new. After delay, you'll see B2. So by banging a filter, the forward path with an impulse, you can actually reveal the internal structure, the internal parameters. But if you do this with an IIR, okay, you bang it, you will see that these things will keep resonating because the Y case will always keep reappearing. There will be non-zeros in output. So you'll get an infinite impulse response. And actually, it's you know, a difficult problem now to derive the structure of a filter if it's IIR from the impulse response. Okay, you can always approximate this with very long forward filter, but this is really very compact. So this is the resonance. Why resonance? Because it kind of keeps back and forth, you know, kind of wave bounces back and forth in this resonant chamber, and it kind of can decay very slowly. So this is what the infinite impulse response stands for. Okay, it's really not so much real for the explanations of the polynomial structure, but these are the two components of this general IIR filter. This is the forward path. This is the resonant or the autoregressive path. Now, if we accept the idea that these are, this is a polynomial, right? Z's to the power of something. This is a polynomial. We can always solve them because we have m roots of this polynomial, n roots of this polynomial. So these will be the roots, okay? Q will be the roots of the top part, okay? Numerator, and then, sorry, nominator, and the bottom will be the roots of the denominator, okay? We can either write them this way, or we can rewrite them by basically, again, moving outside the z to the power, whatever the rank is. But you can see that what we have is this expression, okay? Now, why did we do all of this? And of course, there is much more that people do than plot this curve, this like response. But I find that this is kind of the most intuitive way to explain, especially in the context of source filter model for speech. So let me kind of summarize, or before we move forward, summarize what was the goal, that how we got here. So the idea was we want to build a filter that has formats, okay, have these amplifications in specific locations, okay. We want to do this using this filter. So then the question is, how do we design a filter that actually has the amplifications in the right places? So this is the general form of a filter. And what we see here is just the absolute, right? We need the absolute value. This is the amplification, the gain. We don't really care about the phases at this point. So basically, if we take the absolute value, we can see that what contributes to the gain is basically the distance from z to the pole. Okay, so whenever the z comes closer to q, q are the zeros and p's are the poles. So the distance between z and the zero, right? The closer they get, the lower will be this number, right? I mean, smaller numbers here will be basically points where we have a dip. We have basically a null or a notch in the filter. And the opposite is here. Whenever z gets closer to p, this number becomes very small, but the h becomes very big. So whenever the z comes close to p, this will explode, okay? This is the whole idea. And again, in our speech model, we really don't have anything here except for a constant, because it's really modeled as all pole filter. So there is no zeros really. I mean, we might want to add zeros to get a smoother or more precise structure of the filter. But the whole idea, and this is what we did in this synthesis, in this exercise, we'll just delete erase this, right? So what we did in the homework, and this is the part that I kind of included in the review, was we used this trick, okay, to position the poles in a certain place, and this is the reference, okay? So what we're trying to do basically is design a filter here, okay, which has only poles, okay, so that the frequencies where we have the peaks, okay, or the formants, okay, will be at the right frequencies. So the peaks or the amplifications will be in the right position. Now, this graph is really, I find it very handy and intuitive way to understand how this is related to amplifications, because what it tells you is, and if you remember, we always said that the z's have to move on the unit circle to have the meaning of frequency, right? So if z is e to the j omega t, this is where we move on the omegas, right? So the omega is the frequency here. If we want to put a peak, okay, resonance at a certain frequency, we need to put the pole at that frequency, and the frequency will be the angle here. Okay, so this is what we do. Okay, forget about the zeros right now, but basically the peak is inverse proportional to this distance between P and this Z, which is that frequency. So if at a specific frequency we put Z here, okay, that's our Z, and we look at Z minus P, which is this little interval here, okay. So if we put the Z here, okay, that will be our desired Z, which will be this E to minus J, right, omega T that we desire, okay? So we need to find that omega, okay? So this omega is basically this angle here, okay? So if we put this right angle, the distance here, okay, is going to be this, okay? I hope this drawing can make sense. You have to follow so my explanation as I was drawing, but this is kind of the whole idea that this is the frequency here, omega, right? And basically T, right? We have, because this is omega, so we can think about this as, right, the sampling frequency. So we have basically, so, sorry about that. So we have our T, which is 1 over the sampling frequency, right? And then if we want to think about omega as a frequency, which is 2 pi f, so what we basically get is this angle, right, becomes just the fraction of f over fs times 2p, right? And so this kind of reminds us this whole idea of the sampling is that we basically, this is our 2 pi, and this goes to Nyquist, and this goes back to the sampling frequency, right? And it's kind of a very elegant once you kind of get used to all of these terminologies. But if you think about this going from 0 frequency to Nyquist, okay, this is the angle that you get, okay? So that frequency, okay, we position it pole, so it will be that distance from, you know, this point, that frequency on the unit circle to the pole will give me this desired distance here, and that will be the amplification, okay? This is what happens. I mean, the zero goes the other way. The zero creates zeros. The zeros create the notches here, okay? So anytime you get close to the zero, you actually get a decrease in the response. Every time you get close to the pole, you get an increase in the response. And this is how you basically can design your filters in some kind of a graphical, intuitive way, okay? So yeah, it was kind of, when we went through this, we went very quickly, but we did provide, I think I move forward with the slides. Maybe I have to cancel and erase everything. Should be going to clear. Okay, so I'll clear the drawings and then move forward. Come on. Yep. Okay. So this is basically what I want you to understand, or at least know where it came from. Okay. This whole idea of this function voca, which takes the frequency that you desire. Okay. It also, you can also estimate, you know, the bandwidth by thinking how far it is. It puts you up in that data. That's just what we wrote before, right? This is the frequency where you desire the formant to be, is translated to this angular frequency, or the angle on the unit circle. This is this, okay? And then, because it's an angle and we want to express this as real and imaginary, so we have the real and we have the imaginary component for this spot here, we translate this into complex number, the pole, okay, by having some radius and having an angle. So this is basically a polar representation of this pole with a radius r, and in this case the radius is calculated from here, from the 0, and the angle. Now, how do we translate this to from polar representation to poles and zeros? So we were using signal processing package here that has this ZP 0 poles to TF. So we didn't really explain how this translation is done, but this function basically takes this 0 pole representation, okay, and takes the 0 pole representation and basically opens it up. It basically does this representation, turns this into these A's and B's. Okay, so this is what the function does. It does this translation. Okay, this algebraic manipulation from going from representation of a polynomial as a product of all the roots, right? So numerator and denominator into this. That's what it does. But we basically represented now the poles. For every pole, we need to have the conjugate. That's, I think I mentioned this a little bit, because if you want to have real A's and B's, in this case, we're talking only about the A's because of the poles. If you want to have real coefficients here, okay, you always have to have, for every root, you also need to have the conjugate root. So you create both of them, and this is the filter that we get. It's a very long explanation, but I hope that it kind of explains what we're trying to do here. And this is basically to set up the filter by fixing the poles for that specific frequency, okay? The bandwidth is kind of a little bit of a hack, just telling you where to position this along this axis. Basically, the bigger the bandwidth, okay, and the farther away you be from the 0. If you want to have a 0 bandwidth, R will be 1, you'll be positioned here. But if FB keeps growing, this number will go down. This is sort of just a mathematical attempt to model or give control over how steep will be this peak, because the closer you are, the less the distance from the unit circle is, and because it's in the denominator, it will be higher peak. So this is the radii, this is the angle, this is basically just writing this out as a complex number, and this takes all of these poles and translates into filter coefficients, and then you plug this into a filter, and that's how you run the speech. When you basically filter this with another signal, and the signal itself is this excitation that can be either voiced or unvoiced. So I hope it kind of like brings everything together, kind of sort of just rather abstract way of dealing with filter design, but in the context of formats, I think it kind of does make sense. So yeah, that's a little bit of a review and in-depth explanation of the pole zeros and the graph that we use kind of to get this design in a little bit more of geometric, or you can actually graphically design filters this way on a piece of paper with a zero circle and kind of feel how it goes. Okay. All right, so I'll turn to questions now.